Okay, let's see if we can do this now. Uh, in Chapter 2, you start talking more about the atmosphere and its origins, uh, composition, structure. So we're just going to start very simply. Just what is the composition and structure of the atmosphere? Well, the atmosphere, it covers the whole Earth. So what impacts in one part of the atmosphere may have an impact in another. The example they used in the book was the Saharan Desert. Believe it or not, sometimes there are thunderstorms or big puffs of wind in the Sahara Desert that blow up a lot of dust. They may not put down any rain, but they blow up a lot of dust. When that happens, sometimes it gets caught, and you can actually see it on the satellite image here. And what that shows is the dust coming across the Caribbean. And this has a major impact, actually, on hurricanes and tropical systems that impact the United States. So weather that impacted over Sahara has an impact on the U.S. And dust obviously can do a lot of nasty stuff. So weather goes from tranquil to severe very quickly. Now, the Earth system, if you look at the Earth as a whole, it has an atmosphere, which is what we're going to spend our time talking about, the hydrosphere, which is all the water, the geosphere, which is basically the ground, and the biosphere, which is plant life, human life. And you think about the atmosphere, it's really relatively small. Half of it is contained within 18,000 feet, or basically a little over 3 miles up. So, if you walked along the surface of the Earth for 3 miles, it's not very far, relatively. And if you wanted to go 20 miles, 99% of the mass is already there. So most of the lower atmosphere is pretty uniform. Most of it's made up of nitrogen and oxygen. After that, we get some argon, CO2, water vapor. All those begin to impact into it. But the main two components are nitrogen and oxygen. So oxygen actually stays the same percent too. If you were to climb a mountain, the top of that mountain would have the same percentage of oxygen as the bottom of that mountain. However, the amount of air available to you is a whole lot less, which makes that oxygen a lot less. There are aerosols that impact into the Earth's atmosphere. Water vapor can be up to 4% in the lowest 1 kilometer of the atmosphere sometimes. CO2, we require it for life, but sometimes we get a little bit too much of it. Pollution is another example of things impacting the atmosphere. So one of the things you're going to learn about being in the science course, we'll talk about it some, is we need to think about the scientific method. I want to use an example from meteorology. A few years ago, I was involved in research. We wanted to know why thunderstorms sometimes diminished when they crossed the Appalachians and other times actually intensified. We could never really find a good reason. So that was the question we asked. We could observe this happening. We wanted to know why. So we started to form hypotheses. And one of the hypotheses we formed was that it was connected to the stability and wind shear on the eastern side of the mountain. So we started to analyze the results. And then we went back and observed how those results worked. And we were able to draw some conclusions that actually made some sense out of this. And eventually, they published those results. But what this was a scientific process, a way of looking, making hypothesis, testing it, and retesting it to see if you need to change that hypothesis till you finally come up with something that actually explains the results you're getting. In the weather, we look at things in tornado vortex chambers like Purdue has, automated surface weather systems. We even look at numerical models. Everything I'm going to talk to you about can be explained in numerical models to a point. The National Weather Service has cooperative observer networks that actually look at hail, rainfall estimates, temperature, max, min temperatures. All of that is really designed to look at long term, but it can be, some of that data can be transmitted to National Weather Service sites every day. Radiosondes are lost. What they do is get the temperature. They carry a radiosonde instrument up into the atmosphere. It basically goes up to about 100,000 feet and bursts at that point. The balloon does. It comes back down with a little parachute on it. And these instruments give a vertical profile of air temperature, pressure, and dew point. And here's what they kind of look like. They're pretty small instruments, and they can be tracked. They use a GPS in them now. A dropsonde is a very similar instrument, except it's dropped from an aircraft and goes down drops down towards the ocean typically. And these are used many times in hurricanes. They can also be used in winter storms out over the water. They're not typically dropped over land. They're generally dropped over an ocean somewhere. Remote sensing, we have satellites. We also have radars. Here's a radar tower. And this is what the actual atmosphere looks like. You'll notice in the troposphere, the atmosphere temperature typically drops. Once it reaches the stratosphere, it begins to warm up again. So if you climb a mountain, you're going to find temperature falling as you go up that mountaintop because the atmosphere in the troposphere is always cooling. Once you get into the stratosphere or above the troposphere, however, the atmosphere begins to warm back up until it reaches the mesosphere where it begins to cool, and then the thermosphere begins to warm up again. All these are due to different processes that are happening in the atmosphere. So the auroras, they can be found very simply by the amount of solar wind. The more solar wind that's coming out from the sun, the stronger the disturbance on the magnetic fields, and they may be visible over larger areas. You can see here, much bigger areas some days than others. So really, there are four basic layers to the atmosphere: the troposphere, where we all live and most of the weather occurs; the stratosphere, some thunderstorms can get into the stratosphere; the mesosphere, and the thermosphere. So what I wanted to do just quickly here, this is an upper air sounding. This is Nashville. And if I'm looking at that sounding, there's temperature plotted on the right and dew points plotted on the left. And as it goes up right about here, at about 150 millibars, it begins to warm, or at least not get really any colder. That is the beginning of the stratosphere. So that's about the height of the stratosphere. This diagram is called a Stuvie diagram. It basically just plots temperature and pressure. Pressure is on the y-axis, temperature is on the x-axis. Meteorologists like to do a little bit of change of this. And here is how we change that. Same exact sounding, but now I'm plotting it on a skew T. All I have done, instead of plotting pressure as every equal distance, I have made them a little bit different than that, and I've put the temperatures going to the right at an angle. There's a reason for this that we'll talk about later. But again, you can see the warming taking place right around 200 to 150 millibars, and definitely going up from there. So that is where, today anyways, the troposphere ends. And here's one last map. I wanted to show you a quick upper air map here. And this is just a jet stream blowing along, and you can see the stronger winds here, up here. Most of up in Canada as well. Really not a lot of flow in most of the United States. And think about it. Winds are flowing clockwise here, so this is high pressure in the upper atmosphere. Winds are flowing counterclockwise, there's actually low pressure down here. So let me know if you have any questions about this.